Hi, this is a screencast of a lesson on finding the empirical and molecular formula. First of all, we're going to try to define and identify the difference between an empirical and molecular formula. And then we're going to show you how to calculate those from percentage composition or from lab data. This will be pretty similar to what you're going to be doing in the lab later this week. So the empirical formula is the formula showing the simplest whole number ratio of elements that are in a compound. Okay. Many times the empirical and the molecular formula are exactly the same thing, like water, H2O. That's 2 to 1, simplest ratio. That's also the actual ratio. Sometimes the empirical formula is a simplified form of the actual formula. For example, glucose is C6H12O6. Well, 6 to 12 to 6 can be simplified to 1 to 2 to 1. So the empirical formula for glucose would be CH2O, 1 to 2 to 1. So one of the things that's important is being able to recognize when something is an empirical and when it is a molecular formula or when it's both. So these are all actual formulas. These are all molecular because they're actual. But what I want you to identify is which ones are empirical formulas and which ones are not. So pause the video, take a second, just yes, no, and then restart and check your answers. So if we look at these, if it's an empirical formula, it has to be the simplest ratio. These are all molecular because they are actual molecules. But if it's empirical, it's also going to be the simplest ratio. Like water, yes. This is an empirical formula because 2 to 1 is as simple as it can get. Now, the next one, N2O4, that's an actual molecule, but 2 to 4 is not simplified. So this is not an empirical formula. Here's the glucose that I was talking about, 612,6. That's a no because that can be simplified. Now, the next one, sulfuric acid, sometimes people look at this and they think, no, that's not empirical because they're seeing the 2 and the 4 and they're thinking about simplifying it. But remember, when there's no subscript behind an element, like sulfur is an element, remember that that's a 1. So this is really 2 to 1 to 4. This is indeed empirical because 2 to 1 to 4 cannot be simplified. And then the last one, 2 to 5, that is an empirical formula because 2 and 5 cannot be simplified, not and still have whole numbers anyway, right? So out of the ones on the list here, they're all molecular formulas because they're actual formulas for molecules, but only 3 of them are in empirical form. What we're going to do for the next few slides is show you how to calculate an empirical formula for a compound given percentage composition information or some data in the lab. So these are the steps, and these steps are going to be on the next slide as well when I show you an example. But what I wanted to tell you here was that these two you're always going to need in every empirical formula problem. The first one, this one is only if you start with a percentage composition that you need to do that one. And the last one is if you don't have whole numbers after the first 3 steps, then you need to look for a multiplier. And I'll show you examples of when you do and don't need that first and last step. So looking at this, and there's those same 4 steps. We are starting here with a percentage composition. So we do need the first step. We are going to assume that we have 100 grams of this compound. If it is 88.9% copper by mass, that means that I would have 88.9, and I'm going to erase and let me use the pen because I just don't have enough room to be. So that means that I have 88.9 grams of copper if I have 100 grams of this compound. And that means that I have 11.1 grams of oxygen because remember, percent composition is a mass ratio. Now, you might look at that and say, oh, the formula is 8 coppers for 1 oxygen. But remember, that's a mass ratio. When we write a formula, that has to be a particle ratio. What represents particles? Moles. And that's why in step 2, you have to convert all of the grams to moles, because moles represents Avogadro's number of particles. So if we want a particle ratio, a mole ratio will give us that information. So we're going to convert both of these to moles. This is a skill that you learned in the beginning of this unit. So we know, I'm having a little trouble with my pen, sorry. We know that 1 mole of copper is 64 grams because we looked that up on the periodic table. And we know that 1 mole of oxygen is 16 grams. Okay. So we're going to do those conversions, to divide by the 64. We've been practicing that. And I'm going to keep 3 sig figs. This is why we've been keeping sig figs too, because it's important here when you're doing this kind of problem not to round off too much because it'll guide you to wrong answers. So we want at least 3 sig figs. So I'm going to keep 1.39. Okay, that's moles of copper. And 11.1 divide by 16, and I got 0.694. I'm keeping those 3 sig figs, moles of oxygen. Okay. Now, once you do that step, so we have assumed 100 grams. We have converted our grams to moles. The third step is divide them all by the smallest answer. So 0.694 is the smallest. So we're going to divide every answer. If we had 3 answers, 4 answers, 5 answers, we would divide them all by the smallest one. That's because what you want to do is see how all the other elements compare to one of the elements. And whichever one's the smallest, you want to divide by that, so you get 1. So for this other one, when we divide, we're going to get 2 point something. Well, that's pretty much 2, because I forget the exact number. Hang on here a second. We get 2.0028. That's close enough to round off to 2. And what this tells us is that we have 2 atoms of copper for every 1 atom of oxygen. So now we can write a formula. We know it's 2 coppers for 1 oxygen, and we don't write ones. Remember that? But this is our empirical formula for this particular compound. I didn't need the last step, not needed. Why not? Because 2 and 1 are already whole numbers. Okay. But I will show you an example of when you do need that last step. So let's try another one. This is from your textbook. Okay. So you should be taking notes, examples of how to do these, so you know how to do them in the lab when you do it later this week, and in the homework that you're going to do tonight. So this is the question. I put that in so that you can kind of refer to that area of the textbook as well. So this one, we're already starting with how many grams of iron reacted with how many grams of oxygen. It's not a percentage. So we can skip the first step. And we can just start with these numbers that we are given. Okay. I'm a little trouble with my pen here. So 174.86 grams of iron. And then 75.14 grams of oxygen. So remember, next step is convert them both to moles. So a mole of iron is 56 grams. And a mole of oxygen is 16 grams. So you do this math, you take the 174.86 divided by 56, you get 3.1225. I'm keeping at least, look at this back here, this number that you started with had 5 sig figs, so I'm keeping 5. And then the 75.14 has 4 sig figs. Divide by 16, I'm going to keep 4 sig figs. 4.696. Okay. And then divide by the smallest is the next step. So this is the smallest one, 3.1225. And up here I got 1. And down here I get 1.5. Okay. When you divide the 4.696 by the 3.1225, you get 1.5039. That's close enough to round it off to 1.5. You cannot round that 1.5 though up to 2. Okay. This is a situation where we need that fourth step because oxygen is not a whole number. And we can't write a formula Fe1O 1.5. Remember, in formulas, all of our subscripts, they are always whole numbers. So remember when you have a ratio like 1 to 1.5, you can multiply by anything you want, but you got to do it to all of them. So if I double this one to make it a whole number, I got to double this one as well. So it's really 2, and then over here, instead of 1.5, it's 3. And that's my final answer here, Fe2O3. That's that, I think, hematite that was in the one other question of the previous homework. So one more to practice. You guys give this a try. There's 3 elements. You just do the same thing. It's just you're going to have to convert all 3 of them to moles and divide all 3 of them by the smallest. So pause this, okay, and go ahead and give it a try, and then restart the video and see how you did. So these were all percentages. So I assumed that I had 100 grams, and that meant that the percent represented the mass out of 100. So I'm going to divide them all by their molar masses. This is where it's very important on the periodic table that you get the right molar mass. You get the wrong molar mass for one of these, and it's not going to work out for you. So when I divided all of these, so for the top one, they all have 4 sig figs. So I'm going to keep 4 sig figs. I got 0.4504 for the magnesium. I got 0.9009 for the chlorine. And I got 3.604 for the oxygen. Now you can label them, but what we're really interested in is the numerical ratio. And I'm running out of a little room here. So I'm just going to move on to the next step, which is divide them all by the smallest. And the one that was the smallest was the 0.4504. So up top, I get 1. For the chlorine, I got a 2. And for the oxygen, I got an 8. Whole numbers, so I don't need the last step. So we have 1 magnesium, 2 chlorines, and let me fix that. 2 chlorines and 8 oxygen. Now this is an answer that I will accept and give full credit, okay? But maybe some of you that know your ions a little bit better than others are starting to recognize some of the ions. Magnesium makes a +2 ion, and there is a -1 ion called perchlorate that is ClO4 -1. This compound can really be rewritten. It would be 1 magnesium and then 2 perchlorates. This would be the most proper form for your answer. And it's still 1 magnesium to 2 chlorines to 8 oxygen, but now it's written in the proper form for an ionic compound. Okay. I'll give you credit for this though, because you did establish the right ratio. So does it matter what order you put the elements in? I would generally put them in the order they are listed in the problem. For ionics, the metal always goes first. So put them in the same order that they were listed in the problem when you are doing your practice problems. Now, what's a molecular formula? Well, that's the formula showing the actual number of each element that's in the compound, okay? So sometimes that's the same thing, like the water, or another one is carbon dioxide, right? CO2 is the simplest form, but that's also the actual formula for a molecule of carbon dioxide. Other times, it is a multiple of the empirical. Like if you did an empirical formula calculation for glucose, you would get this, but the actual or molecular formula is, remember, the C6H12O6. There's a multiplier, and in this case, it's 6, that gets you from the empirical to the molecular formula. So I need to show you how you can determine the multiplier with information that you will be given in the problem. We're going to do one sample together, and then I'll have you do a sample on your own, which we will go over. So the molecular formula is a multiple of the empirical. To find the multiple, the multiplier, you take the molar mass of the compound and you divide by the empirical mass, okay? That's going to give you, this is going to be a whole number. And this is your multiplier, okay? And once you get that multiplier, you multiply every subscript in the formula, just like we did back here. Like if we figured out that our multiplier was 6, we took 1 times 6. We took 2 times 6. We took 1 times 6 to get the molecular formula, okay? So let's do that in an example. All right. Here's the type of problem that you will be given. The first thing you have to do is determine the empirical formula. You have to know the empirical formula to figure out the empirical mass and to figure out what to multiply. So there's another one. We'll do this one together. It's another one that's given by percentages. This is another one that sometimes people just want to write 4:1. But that's not it, because that's a mass ratio. And remember that formulas are always a particle ratio. So we know that a mole of carbon is 12 grams. I have a little spot on my screen sometimes that gives me issues. So that says there, that's a little better. 1 mole and 12 grams. And then the hydrogen, 1 mole weighs 1 gram. So this is easy. 20 divided by 1 is 20. So 80 divided by 12, I get 6.67. So I've done the first 2 steps. I've assumed that I had 100 grams. I've converted to moles. Now I divide by the smallest, and I get 1. Divide by the smallest, and I get 3. So the empirical formula is CH3. This is the empirical formula, right? So to find the empirical mass, once you determine the empirical formula, you do a little mass problem. So I'm going to do that right here. Like carbon, we got 1 times 12. That's 12. Hydrogen, we have 3 of them. It weighs 1, so that's 3. So this is, right? This is the empirical mass because it is the mass of the empirical formula. So if the molar mass is 30 grams per mole, what's the molecular formula? So remember that to find the multiplier, you take the molar mass and you divide by the empirical mass, and you should get a whole number. So if you look here, the molar mass is given in the problem, and it's going to be given in the problem. There are ways to find it. We haven't gotten there yet, okay? So the molar mass is 30 grams per mole. So it's 30 grams for the molar mass. The empirical mass is 15 grams per mole. That's easy. That's going to give us 2. So our multiplier is 2. Instead of 1 to 3, that makes our formula 2 to 6. And this is the molecular formula for actually ethane, okay? Now you try it. Here's some info. What you want to do is get a piece of paper and a calculator and your periodic table. You probably should have already had all that stuff. But try this. Okay. Hit pause and try it. And then after you are done, restart and see how you did. So hopefully you can tell this is 12. There, that wrote a little bit better. And this says 1 mole right here. There. Okay, so 92.3 divided by 12 is 7.69. 7.7 divided by 1 is 7.7. Divide by the smallest, I think you can see, we're going to get 1 to 1. So the empirical formula is CH. Okay. Now to get the empirical mass, right, we have 1 carbon, 1 times 12. We have 1 hydrogen. And the empirical mass is 13. So now to get our multiplier, we take the molar mass, which is 78, and we divide by the empirical mass, which is 13. 78 divided by 13, the multiplier is 6. Instead of 1 to 1, we get 6 to 6. This is a molecule of benzene. So you hopefully can tell the difference between the empirical and the molecular formulas. The empirical formula is the simplest ratio. Every single subscript has to be in the simplest form. The molecular formula is an actual molecule. It may be the exact same thing as the empirical, or it might be a multiple of it. To get the empirical formula from a percent composition or lab data, you had 4 steps, and the second and third step are required. Convert to moles, divide by the smallest. To get the molecular formula, okay, you got to find the empirical mass, and you have to take the molar mass and divide by the empirical mass to get the multiplier, and then take your empirical formula times that. Good luck with the homework, and keep these notes and examples handy for the lab.